Hello everyone, my name is Françoise Triboulet. In EASA, I am contributing to the EASA AI program led by Guillaume Soudin. One aim with a project named AI Assurance is to identify the objectives that an applicant will have to satisfy in order to maintain our industry's recognized level of safety, or even to take advantage of the safety benefits we might expect from the technology. Today, in the context of my participation to WG-114, I shall address one activity which took place after the first issue of the EASA AI concept paper in December 2021. As the standard was maturing and EASA was preparing the issue 2 of the concept paper, bidirectional mapping of the objectives of the concept paper to from the objectives of ED 324 ARP 6983 could be established, allowing a stepwise alignment. For illustration, here are a few topics that were discussed. Let's start with data labeling, which corresponds to establishing the ground truth. Data labeling was upgraded from an activity to an objective, part of the data management process. EASA's view was that this activity was so important that it deserved an objective. At the end of the day, the group took a similar approach. Another important alignment was concerning the robustness of the ML model. This topic necessitated first an alignment on the notions of edge and corner cases inside the operational design domain. Once the alignment could be reached, the next step, consisting into aligning the text in the draft standard and the objectives in the EASA AI concept paper, became obvious. If an initial level of alignment could be achieved, we are not at the end of our journey. For example, during the last plenary in Retafe, we could align our views on the proportionality of some objectives with regards to the criticality and assurance level allocated to the machine learning constituent. In Insight, we are confident that we will continue our efforts and we will converge towards a standard that will be a strong asset for our industry. Probably that most of you know that EASA has entered into rulemaking since second half of 2024 with the launch of rulemaking task 0742. As we progress drafting the first notice of proposed amendment, we take provisions in case the standard would not be timely available. However, our ambitions remains to be in a position to recognize this standard should the timing be compatible with the one of the rulemaking task. As you can imagine, I'm looking forward to continuing to work on these exciting and challenging subjects.
Hello everyone, my name is Sandrine and I work for Airbus Commercial in the certification of cockpit and avionics systems. So please forgive me if I may focus on the airborne domain in this video, as our document also covers the ATM ANS domain. I am the co-chair of the EUROCAE Working Group 114, joined with the SAE G34 committee. I also co-lead the subgroup related to systems, safety and process considerations, known as SG57. In the episode 6 of this EUROCAE video series, my colleague Emmanuel presented the machine learning constituent concept, MLC concept, and the main challenges related to its integration within the system. In this episode and the next, myself and my SG57 colleague from SAE, Ganesh Pai, will both give you a deeper insight of the MLC impact in the system processes. Although the EUROCAE ED 324 and the SAE ARP 6983 is about processes for development and assurance of artificial intelligence, and in particular in the first issue of the document machine learning, when integrated into aeronautical products, the starting point for this work is at a system level. For the most part, the system development and safety assessment processes are largely going to be applied as usual, meaning that the existing recommended practices apply. However, some adjustments are to be expected for accommodating the particular considerations that machine learning brings. There are 4 system considerations that are noteworthy. First, relating the system operating environment definition to the definition of an operational design domain, known as ODD, for the MLC and also the ML models. Second, defining performance requirements at a system level that can be translated into performance metrics relevant for evaluating machine-learned functionality. Third, adapting the system architecture to cope with ML specificities and in particular the safety concerns due to insufficient MLC performance. Lastly, the integration and verification of the MLC into the overall system. I will focus on these last two considerations in this video, and Ganesh will describe the first two ones in the next video. So, for the system architecture, it's important to remind that in the system hierarchy, the MLC addresses the lowest level of a functional breakdown. Developing a system architecture to integrate ML constituents is an iterative process, which requires a deeper than usual collaboration and coordination between the system and safety engineers and data scientists. Together, we can reflect the impacts of data collection, ML model properties, and implementation constraints in the system architecture such that there is a well-defined and bounded system structure that meets the established system requirements. To do this, we may define mechanisms such as novelty detection for input validity or confidence scores for output validity as interfaces that accommodate the specifics of ML. We may also include protections such as operating environment monitoring or independent external monitoring of the MLC, or even contingencies when there is a degradation of MLC performance. Overall, the system architecture is crucial to recognize, record, and manage potentially unintended behavior that may emerge due to an MLC. For the system-level integration and verification, the key focus that is somewhat different from the conventional process is the additional phases necessary on the operational condition and constraints. Those conditions may affect the overall performance of the integrated system. For example, when the ML model gets input sequences in operation, which are different from the sequences of data that were used during its training. Additionally, the data used during the MLC development process may also present some emergent behavior, and system integration is critical to expose and mitigate this potentially unintended behavior. I hope you enjoyed this video. I'm really proud to work in this joint SAE EUROCAE committee with many experts in various fields working together constructively and with other standardization groups. This is one of the keys to successfully build such an innovative and ambitious process standard. Thank you for watching and stay tuned.
Aloha, I'm Ganesh Pai and I'm a Senior Technical Fellow for Safety Assurance at KBR. I'm also a contractor member of the scientific staff at the National Aeronautics and Space Administration's Ames Research Center here in California. I've been involved with SAE G34 since 2021, and currently I'm one of the co-leads of Subgroup 57 or SG57, addressing systems, safety, and process considerations. I'm also a co-author and co-editor of several sections of ARP 6983, cross-listed as ED 324 on the EUROCAE side. For more information on the committee and document structure, please check out episode 2 of this video series. In a previous video, you heard from one of my EUROCAE co-leads for SG57, Sandrine, and she listed 4 important systems considerations, describing 2 of them, namely the system architecture and systems integration and verification. In this video, I would like to give you some more information on the remaining 2 of those 4 considerations. The first consideration I would like to discuss is about the operating environment for the system. Basically, we need to better define the operating environment of intended use, and the main purpose is to be able to support a lower level data-driven process known as the ML constituent development process by allocating and assigning it the information that is necessary about the operating environment from the system level. Essentially, we want to be able to refine the specification of the operating environment to a level of detail that is sufficient to define the operational design domain for the machine learned functionality, also known as the ODD. The ODD, simply put, is a specification of the input space being considered for the design of the ML constituent and the underlying ML models. Ideally, we would like the ODD to be the same as the operating environment, but often it is a restriction of that operating environment. Effectively, we will define the operating environment to a greater level of detail than what we normally do, but this is crucial to support the data collection activity of the lower level ML constituent development process. The second consideration of importance is the definition of performance requirements. And since machine learned functionality is typically evaluated using quantitative performance metrics, we need to clarify the relationship of those metrics to system safety and to the intended behavior at the system level. Here, some of the questions that we would like to answer are the following. How do we go from system safety objectives to performance requirements on the machine learned functionality? Which metrics do we select or define? And what values are suitable for those metrics? And another critical question is, how do we know that the metrics that we have defined are valid? The approach that our document is taking to answer those questions is to require the definition of system-level performance requirements that include safety-related metrics and the related tolerances, thresholds, and bounds. These are then translated into the appropriate performance metrics for the machine learning model and the machine learned constituent in the ML constituent development process, which is then validated together with systems processes. And in an effort known as quantitative safety assessment, or QSA, we worked on a perception use case to inform the guidelines that we're authoring for this effort. I hope that this short video has given you some more insight into what we have been doing in our joint SAE EUROCAE committee from a systems development and safety standpoint when integrating machine learning into aeronautical products. I want to emphasize that although I am one of the faces of this effort, as in this video, the document that we're authoring is the result of the hard work of many competent committee members who have been contributing their time and their expertise on a regular and constructive basis. So I would like to take this opportunity to thank all of them for their efforts and support and say mahalo.